Now we will consider uniform circular motion. Uniform circular motion means my particle moves along this circle at constant speed. So this is uniform circular motion. This is not uniform circular motion. If it moves along at constant speed, if its exact velocity at each moment, exact speed is 1 centimeter per second, that's uniform. This, okay, this is not uniform. So we understand that. If it's doing uniform circular motion, the distance is increasing at a constant rate. So the angle is also increasing at a constant rate, and we have here theta equals omega t. Okay? Constant angular velocity. What is the dimension and unit of this omega? It's pronounced omega, not W. Okay? What is its unit? Well, the unit of theta is radian. Radian per second. Okay? Now, the total distance gone, S, along the circle, is the speed v times t. Okay? But at the same time, S is r times theta, which is r times, for uniform circular motions, r times omega times t. So v is nothing but omega times r. Okay? And omega is just the meter per second speed or velocity divided by r. Is this clear? Period t, time to cover full circle, is the distance gone, 2 pi r, divided by the velocity, v, okay? Well, how much time will that be? It's simply 2 pi over omega. Or omega is 2 pi over t. And this is clear because one full term in radian units is 2 pi radians per t seconds. So that's the speed. If t is 5 seconds, 2 pi over 5 is the radian per second angular velocity. Clear? We have another concept, the frequency. F, what is it? It's how many full turns per second. Okay. For example, if the period is 5 seconds, F is 1 over 5, which is 0.2, 1/5. What does that say? Well, in 1 second, 1/5 of a period is covered because the full period is in 5 seconds. If the period t is 0.01 seconds, then the frequency is 1 over 0.01, 100. It means the period is 100 of a second. The frequency is 100 times per second. Okay? What is the unit of that? Unit of it is second to the minus 1, or cycles per second, CPS. And sometimes it's called hertz. In terms of omega, which was 2 pi over t, omega is just 2 pi times f. Because if it does f turns per second, it means 2 pi times f radians per second. Okay? Any questions about this? Now let us start some more serious stuff. R, the position vector, changes as a function of time. But how do I find R? Well, it's simply x and y components in a plane. We are talking about a circle. A circle is in a plane, so this motion is two-dimensional. There is no k there. I just choose an x-axis and a y-axis, and this is my motion. Okay? Now, as my particle moves along the circle, its x position is this. X is, what is x in terms of r and theta? It's r times the cosine of theta, right? And what's y? Y is r times sine theta. Okay? So now let's go back to our last page. It's r cos theta, that's changing, plus sine theta. Okay. Now I can go one step further. For uniform circular motion, I know exactly how theta changes as a function of time. Let me put that in also. R is a constant, just the radius of this circle, and I have here cosine omega t plus sine omega t. Okay? Okay, now here we have an expression for the position vector, both x and y, of an object doing uniform circular motion. I know the position as a function of time. If I know the position as a function of time, I can calculate the exact velocity as a function of time. Right? Let's do that. V of t is simply dr dt, which is r